Okay, I guess we are live. So hello everyone and welcome to session 119 of the Latin American Webinars on Physics. My name is Joel Jones from the PUCP in Peru and I will be your host today. We are having Aida El-Khadra as a speaker. She carried out her PhD at UCLA, which was followed by postdocs at Brookhaven, Fermilab, and The Ohio State University, all in the USA. She's currently a professor at the University of Illinois, Urbana-Champaign. So today, Aida will talk about the anomalous magnetic moment of the muon, which is a topic you probably have heard about. And we are very fortunate to have her today, as she is a co-chair of the Muon G-2 theory initiative. So we're very happy to have you here. So before we begin, let me remind all viewers that you can ask questions and make comments via the YouTube live chat system. And these questions will be passed on to Aida at the end of her talk. So thank you once again for being here, and we're all yours.
Thank you so much. I am delighted to be here. It is truly a pleasure to give this talk and to reach down to the Americas, all of them. I am delighted to be here and just also really happy to participate in this. So I am going to tell you about the anomalous magnetic moment of the muon. Here you can see two iconic pictures of the experiment at Fermilab. And here you see a picture of when the muon magnet ring arrived at Fermilab to begin taking data. So here is an outline of my talk. I will start with an introduction, tell you a little bit about the overall global situation, and then tell you a little bit more about the theory initiative and the standard model contributions before delving into more detail into the hadronic contributions with the two methods, and then conclude with a summary and an outlook. So first, just to get started, to put us all on the same page, as a reminder, we're talking about the magnetic moment of an elementary particle that also carries electric charge. So the muon is just one of three charged leptons, the electron and the tau lepton being its siblings, being distinguished by their masses. So the combination of electric charge and spin gives rise to a magnetic moment, which in the Dirac theory was predicted to be to have a prefactor, a G factor equals to 2. Once one includes quantum corrections, loop effects, then the vertex is modified to this form where via acquiring F2 of 0, acquiring from quantum loop effects, a non-zero value now leads to deviation of G from 2, which is parameterized as the anomalous magnetic moment. A is defined as G minus 2 over 2 is exactly equal to F2 of 0. So F2 of 0 can be computed in the standard model by computing all possible loop contributions to this vertex from all standard model particles. As such, of course, this quantity is very interesting. The anomalous magnetic moment, as you see by definition, arises due to loop effects. So anything that is only sensitive to loop effects in the standard model, by definition, would also be sensitive to the effects of new particles not yet observed. And in particular, if you look at the structure of this vertex here, you will see that muon in, muon out. This means, of course, this contribution is flavor conserving. It is also CP conserving, and it flips chirality. So in terms of probing new physics effects, this one is complementary to some other effects say, CP violating effects, etc., or flavor violating effects. So it is also from that point of view an interesting complementary probe. Let me now go to a little bit to the history. So one of the reasons why the muon magnetic moment is so interesting and receives so much attention is because there's a long-standing difference between standard model expectations shown here and prior to the Fermilab experiment coming out with their new measurement, the most precise measurement came from a Brookhaven experiment that concluded 20 years ago and left us with a tantalizing but inconclusive tension of somewhere between 3 and 4 sigma. When this result came out, of course, that spurred more theory evaluations, and so standard model theory has gotten more precise in the intervening 20 years. It hasn't moved, which is also significant. And now we have a new experimental measurement by the Fermilab experiment. What the Fermilab experiment did is they took the ring that was situated at Brookhaven and moved it to Fermilab. They recalibrated it and redid everything, made this in a much better instrument than it was at Brookhaven. It is fed by a higher energy and higher intensity muon beam. So this is really a brand new experiment using the same experimental methods as the Brookhaven experiment. And they released the measurement result from their run 1 data on the April the 7th of this year to great international media attention. And I will tell you in a second why. Also significant is that they already have the data from their runs 2 and 3 in the can, so to speak, and that analysis is ongoing. And they're currently running also, they're currently started run 5 or are about to start run 5 soon. So a lot more data will come from the Fermilab experiment. Now, what happened and what was so super exciting when on April the 7th, when the Fermilab experiment revealed their new measurement, first, their measurement is in complete agreement with the Brookhaven measurement. So that by itself is, just an amazing success of a really beautiful experiment. And then second, it increased the significance of the tension between standard model predictions and the new experimental average, now to an even more tantalizing 4.2 sigma. What I will do in this talk is tell you about what goes into the standard model predictions and what are some of the tensions and puzzles here. As a theorist, I don't have much more to say about the experiment other than more data on the way. There will also be an experiment that will take data in Japan, the J-PARC experiment. Excuse me one second. Which will start taking data in the latter half of the 2020s using a completely different method from the Fermilab experiment. So the experimental situation will be well in hand. Here's a timeline of the plans for the experimental measurements and release of the data. What is really exciting about this is that we don't have to wait another decade or two to know a lot more about the experimental measurement of this quantity. New measurements are right around the corner. They will get better. The measurement that came out from Fermilab is statistics dominated. So the prospects for learning a lot more within the next 5 years are very, very good indeed. The prospects that we will have total error on the experimental measurement reduced by a factor of 4 within 5 years from now is, are really good. So that means that theory needs to keep pace. And that was one of the aims of the Muon G-2 theory initiative, is to address the experimental progress and bring the entire theory community, I should say theory and experimental community together to have a, comprehensive assessment of the various theory uncertainties that go in and make the theory predictions, the standard model theory predictions, more reliable and also more precise. So by putting all of the disparate communities together, we learn more. So for that purpose, the theory initiative got going in 2017. We've already had over a half a dozen workshops. The last one was a virtual workshop that was held at KEK, and we're planning another workshop next year because we're planning to update our white paper. The first white paper of this initiative came out in June of last year and is the basis upon which the experiment compares to standard model theory. The effort is led by a steering committee, which also represents the diversity of the effort, both in terms of internationally, you see that people are participating from all over the world, also in terms of the diversity of the different communities that participate, having contributions from both, from lattice theorists, from dispersive theorists, and from experimentalists that provide the experimental inputs. I should mention that the community, and in fact, the community of people working in low energy experiments and hadron physics suffered a great loss earlier this year with Simon Eidelman, who was a member of the steering committee and involved in many experiments, relevant experiments, passing away rather suddenly. He is going to be very, very hard to replace. So let me now go to telling you about the ingredients of the standard model prediction of the anomalous magnetic moment. It is usually broken down into QED and then electroweak, being focused on the weak bosons and Higgs boson, etc. contributions, and then the hadronic contributions. Starting with QED, this is a story that spans several decades as well, of an amazing heroic effort to compute the QED contributions through fifth loop order, which involves tens of thousands, over 10,000 diagrams, and results in the QED contributions to the anomalous magnetic moment of the muon now being known to a precision that will never be reached or will not be reached in a very, very long time by the experiments. So it is basically done and known now, thanks to the efforts of a very dedicated community of people. Similarly, for the electroweak contributions, there were dedicated efforts to compute these also with the measurement of the Higgs boson mass. The last contributions could be computed even more precisely. And this is now known through two-loop order, with the remaining uncertainties small, the remaining uncertainties actually being dominated by hadronic loops in the two-loop contributions. But here they don't play a large uncertainty role. The hadronic contributions are the topic of most of the discussions of the theory initiative because they drive the theoretical uncertainty. The leading hadronic contribution comes from the so-called hadronic vacuum polarization, whereby a muon emits a virtual photon, which creates a hadronic vacuum bubble and then recombines. So that's the regular vacuum polarization, of course, as well, but now with a QQ bar loop that creates a hadronic bubble. A contribution that's suppressed by another power of alpha, so is of order alpha cubed, is the hadronic light by light. You can see 4 photons here. That looks like light by light scattering, then connecting to the muon line. That's why this is called the hadronic light by light. So hadronic vacuum polarization enters at order alpha squared. And then in order to meet the precision demands of the experiments, we need to also compute the next to leading and next to leading order contributions, meaning hadronic contributions that enter at order alpha cubed and at order alpha to the 4th. So the contributions are smaller, much smaller than the QED contributions, but they are the dominant, they make the dominant contribution to the theory error. So this is summarized here, where you see the QED contribution, the electroweak contribution, also very small. It's 150 in units of 10 to the minus 11, with theory errors that are basically negligible. Recall that the precision target is 140 of the experiment is 140 parts per billion. So these are basically irrelevant, these uncertainties, but these uncertainties are very much relevant, and that's what I will be discussing. Now note that this is the driving uncertainty, but the hadronic vacuum polarization itself is known to sub-percent precision. In order to make this uncertainty small enough, it needs to be known to about 0.2%. The hadronic light by light being suppressed, you can see its overall size even further. Actually, to address the precision targets, we only need to know it to about 10 to 20% in order to meet the precision demands. Okay, so this is a briefish introduction. So let me now delve a little bit deeper into the hadronic contributions. First, describing you how these are evaluated using dispersive data-driven methods. So just again, as a reminder, we're talking about the hadronic vacuum polarization function defined here, which is then plugged into the loop integral to be evaluated, and the schematic form is given here. So with knowledge of the vacuum polarization function, and this is just the this comes from the loop integral and contains kinematic factors, etc. One then can compute the hadronic vacuum polarization loop contribution to the anomalous magnetic moment. In the absence of being able to compute the vacuum polarization function over all Q² ranges, we need to know this not just at large Q² where we can use perturbative QCD, but also at low Q² where the vacuum polarization contribution is dominated by hadronic contributions, and that is, of course, the difficulty. So one uses the optical theorem and then a dispersion relation to rewrite the integral in terms of a hadronic cross-section, which gives you this expression with a new integration kernel shown here. Again, these are all known equations. I'm not going to write them down. Now we have expressed the hadronic vacuum polarization, at least at leading order, in terms of experimentally measurable cross-sections. And if all of the cross sections that contribute at all of the different center of mass energies are known, then all one needs to do basically is sum up over all of the channels to obtain this. So this then leaves a determination of the hadronic vacuum polarization contribution that is driven by the experimental measurement errors. So this method has been developed and refined over the past 20 years, and the experimental cross-section measurements have also been performed over that long. So there's a whole community of experiments that provide these measurements. Some of them are still active, even though the experiments themselves have long stopped collecting data, for example, like the Barbar experiment, and some have just started collecting data. So this is a good situation because these measurements are needed with exquisite experimental measurement precision, and having many different experimental measurements that can then also be compared to each other is good, so that we are really ensuring ourselves against measurement errors in this important quantity. So here's a summary of 2 of the leading compilations that do these evaluations. You're not meant to read all of the channels. This is basically just an impressionistic view to tell you that basically all of the channels up to about 2 GeV, all of the different hadronic channels have been measured. As some of these measurements are rather recent, some of those high pion multiplicity and other channels, but they're all now measured and can be summed up in the direct integration method. So this is also illustrated here. So this is from the DHMZ compilation, and this is from the KNT compilation with a very colorful mountainous plot indicating all of the different channels and their contributions in this region. And over here in the pie chart, it shows the contributions from these different channels to the value of a mu and the contributions from the errors. What you can see is that it is this region here, the region below a GeV or so, that gives the dominant contributions to the theory error. There's also contributions due to radiative corrections and perturbative QCD, but those are really, really small, comparably small. So the experimental errors in this energy region are very important, and measuring the channels in this energy region, which is dominated by the pi-pi channel, that's the yellow shown here. Note that this is a log plot. So in a regular plot, this yellow would be huge. This yellow contribution would be huge. It dwarfs the other ones mostly. Okay, so what is, however, also going on is in that important yellow region, there are some tensions between the two different data sets that have the smallest overall uncertainties from Babar and Chloe, and that tension needs to be taken into account, obviously, if we take if we want to take these compilations to obtain a mu. This was subject of intense discussions at our workshops, how to do this safely, how to understand the tensions, and then how to deal with them. So the outcome of that at the INT workshop in 2019 was a conservative, what we called merging procedure, in order to account for all of the tensions in the data and also for slight differences that occur when different groups of people make slightly different choices for when do you connect to perturbative QCD, how do you treat the systematic errors exactly, etc. So the ultimate result is then this is the result that came out of this theory initiative effort. And you might note that the total error is not smaller than individual errors from individual compilations, because we were conservative in how we treated the total errors. Now let me talk a little bit more about, let me start talking about the light by light contribution, which is illustrated here. Prior to the theory initiatives efforts, the light by light contribution was estimated using essentially models of QCD, using large N estimates and chiral perturbation theory inspired models, where one then obtains estimates of individual contributions into which this hadronic bubble can be broken up to. The dominant contribution comes from pion exchange, but they will also be higher pseudoscalars, and there's loops and other resonances contributing. The problem is that different models will break these contributions down differently, and this was tried to be estimated using just averaging over all of the different models in the Glasgow consensus. This means that the theory error for this quantity prior to the theory initiative was really not well quantified at all. And people were worried about what if these models are simply wrong? What if the estimate of the light by light is off by a factor of 2? Then it could actually rescue the standard model, and it could bring the standard model into agreement with the experimental measurements. So this was a big question mark prior, excuse me. And now there is a dispersive approach that was being developed in the mid-2010s and refined as a result of the theory initiative activities, which provides for a model-independent approach similar to the hadronic vacuum polarization. It's much more complicated. because you're dealing with a 4-point function instead of a 2-point function. But that framework then allows for a data-driven evaluation if you have enough experimental data. Also interestingly is that one can use lattice inputs, lattice results, lattice calculations as inputs into this dispersive approach. I don't want to spend too much time on this. This could very easily be a long seminar of its own. But here's a comparison table where you see the old data, the old model estimates and their spread. And here you see the results from the data-driven approach, where basically the dominant contributions from the pion and pseudoscalar poles, from the pion and kaon loops and boxes, and pi-pi rescattering in the S-wave are computed using lattice inputs and experimental inputs that are well enough known to obtain these with these relatively small errors and well quantified errors. So these contributions here, this error bar is really well quantified. We know where the errors come from, and the errors, of course, can also be refined. There are still contributions from the larger energy scales that are much smaller, but much less well quantified. And those are the main source of theory errors in the dispersive framework. So it's basically the errors of these contributions. These contributions are taken with essentially 100% error in order to obtain this estimate from the data-driven approach, the data-driven dispersive approach. So we can say now that the errors are almost well quantified, but there are still pieces that need to be done better. So that is the situation of dispersive methods. Let me now talk a little bit about lattice methods, starting with a lightning fast introduction to Lattice Qcd in 2 slides. So in Lattice Qcd, in lattice field theory, space-time is separated into discrete space-time lattice with next to nearest space-time points being separated by a finite lattice spacing. So that's an approximation, and that is needed in order to evaluate the integrals, the path integrals numerically using Monte Carlo methods. So there are several approximations. There's the lattice spacing, which is always called little a, and so that's the same letter we use for the anomalous magnetic moment. So you have to understand what context A we're using. There's the finite volume and finite time extent that also then turns the degrees of freedom into a large but finite number by which we can evaluate the integrals numerically. Now, in order to make contact with the real world, of course, these approximations must be taken away. And the good thing is that they come with adjustable parameters that can be studied. So instead of doing one computation with one set of parameters in Lattice Qcd computations where we want to obtain results with quantified errors, we repeat our simulations, we repeat our Monte Carlo integrations over by varying these parameters. The other thing is that these adjustable parameters all come with an effective field theory that provides the underlying description of QCD. And so the effective field theory then guides the extrapolations or interpolations that is associated with these parameter variations. So the continuum limit is guided by semantic effective field theory. There are effective field theories for the finite volume and time as well. And the approach to the physical up and down quark masses can be described by chiral perturbation theory, for example. So what this means then is that any lattice calculation that claims to be quantitative, to have a quantitative estimate of the underlying uncertainties, must be based on a computation of several ensembles where you vary these parameters. And so over on the left is an example of such an ensemble set that was created by the Milk collaboration. And And this is just showing the ensemble parameters in 2 dimensions. So on the x-axis, we're showing the lattice spacing, and on the y-axis, the pion mass that is given by the masses of the underlying C quarks. So it's showing you this parameter and this parameter here. Obviously, you can also vary these other parameters in simulations. C quarks are only included for the strange and the charm case, and that's what's indicated in the 2 + 1 + 1. The up and down quark masses are degenerate, and that's the 2. And then there is a C quark for the describing the strange and the C quark describing the charm. The charm effect, the C quark effects of bottom quarks can be estimated perturbatively. So this is a large ensemble set. Then what is also shown here is the size of these circles indicates how much time we spend on the Monte Carlo integrations. The bigger the circle, the smaller the statistical error, basically. And then over here is the cyan star indicates the physical point in these 2 parameter sets. You can add more dimensions to show the finite volumes, etc. as well, but this is just an illustration. So with such a large ensemble set with all of these different parameter variations, taking the continuum infinite volume and interpolating to the physical masses is something that can be done reliably with quantified errors. Doing this then is what we mean when we say that Lattice Qcd computations provide us an ab initio picture of QCD. So what is the state of the art? Lattice Qcd calculations have progressed within the last decade to provide us computations of very simple quantities involving stable mesons in the initial and final state with this quantitative accounting for all systematic effects. And we have results of very simple quantities, for example, the decay constant of a pion and a kaon, where the errors from the lattice calculations are at the sub% and also sub-0.5%, like 0.2% errors. In some cases, the errors from lattice calculations of the hadronic quantities that would be needed to compare with experiment are smaller than the experimental uncertainties. So in this background, then it makes sense to also use Lattice Qcd methods for the hadronic vacuum polarization, which has such a demanding precision needs. Okay, so part of this scope then, part of this progress then also means that the scope of Lattice Qcd calculations has increased very rapidly in the last decade of Lattice Qcd computations where the uncertainties are quantifiable. So going back to the hadronic vacuum polarization function, then there's some differences between how this is evaluated when we use Lattice Qcd, where we live in Euclidean space, and one can then rewrite this as an integral over Euclidean momenta or even Euclidean time, as is done here. So in Lattice Qcd, we can very straightforwardly compute a correlation function like this, where this is the electromagnetic current over here as a function of space and time, sum over space to compute this as a function of Euclidean time. So basically here and here at rest. This is the basic quantity that we compute on the lattice, which we can then use via Fourier transform to obtain the vacuum polarization function, or plug in directly and rearrange the integration boundaries to plug it into the integral to obtain the hadronic vacuum polarization. So the currents here, of course, include all of the flavors, the quark flavors that are needed. So a lattice computation proceeds along a different breakdown from data-driven dispersive methods, where we're summing over all of the different hadronic channels. Here we're summing over the different flavors, and it also makes sense to separate disconnected contributions, disconnected with contractions from the connected ones. So I'm showing here these diagrams where implicitly there's a gluon and C-quark background that's not shown. These diagrams are then computed on the quark-gluon vacuum that is produced by the Monte Carlo simulation. So here's the connected and the disconnected diagrams. Since these simulations are obtained in the isospin limit and often without QED in them, those corrections must also be computed and are often computed separately. So because each of these different contributions have their own systematic error analysis and the way that systematic and statistical errors enter, it makes sense to compute the different flavor contributions, disconnected, QED, and strong isospin contributions separately, and then add them all up to obtain the total A mu. So that's the general strategy, how these things proceed on the lattice. And here I'm just giving you a rough breakdown. The light quark connected contribution, not surprisingly, given that in the data-driven approach, it is dominated by 2 pion contributions, provides us with 90% of the total hadronic vacuum polarization contributions, followed by about 10% for strange, charm, and then the B quark contributions are really, really small. Disconnected is about 2%, and the isospin breaking and QED contributions make up about 1%. So the precision demands then of these different contributions are different. For the 90% of the total, we really must compute it with the precision, the ultimate precision that we need, but we can compute 1% of the total with a precision of 10%, and that's good enough. And here's a pie chart breakdown of the different contributions and the error contributions as of the status of the white paper, and you can see the contributions to A mu, the light quark contribution at 90%, etc. And what you also see is that some of the subleading, like isospin and disconnected contributions, we're still not known with quite the accuracy with which we need them to be. So improving those will be important in improving the overall accuracy to the precision goal. And the dominant uncertainty still comes from the light quark contributions. None of this is particularly surprising. So the challenges are then we really need ensembles where the light C-quark masses are at their physical values. And that's something that I have with a check mark, because there are several groups that have large ensemble sets where that is the case. We need to carefully understand finite volume corrections. There is an issue with the growth of statistical errors at long distances. The continuum extrapolation must be understood, of course, at the commensurate precision, and that is rather demanding for a quantity like the hadronic vacuum polarization that receives contributions from all these different distance scales. And then understanding subleading uncertainty contributions and including the disconnected and QED I've already explained. So those are the challenges of the lattice computation. I'm going to skip over this. This is just an illustration of the amount of effort that has gone into to address all of the different challenges. Here, the challenge that is posed by the growth of the statistical errors of the Euclidean correlation function for light quarks at large times, which then dominates the statistical errors. And there are quite a few different solution strategies that will lead to exquisitely precise results in the very near future. I would now like to come to the hadronic light by light computed directly in Lattice Qcd. So computing these diagrams and their disconnected cousins directly. There are 2 groups who have done so, who have completed their lattice calculations of this quantity directly. The RBC UK QCD collaboration and the Mainz group. The RBC UK QCD collaboration published their result in 2020, and it was included in the white paper. The Mainz group posted their result within a day of the Fermilab announcement, interestingly, on Archive, and this result is now published. The two groups use different methods for dealing with the QED contributions. RBC UKQCD includes QED effects in a finite volume, which has of course then an effect on finite volume effects. Those are much more serious. The Mainz group has provided a semi-analytic QED kernel function in infinite volume, so their finite volume effects are the same as you have in QCD. They use different ensembles that they generated independently. In one case, the ensembles are at or near physical mass. In the other case, the ensembles have pions, C pions in them that are larger than the physical pions, and you need to obtain a chiral extrapolation to the physical point still. And there have also been cross-checks between the two groups that are part of the white paper to check the methods against each other at unphysical pion masses. And needless to say that both groups have also debugged their methods by just computing the pure QED loops to see that they agree with the exactly computed perturbative results. So all of these checks have been done, and we are now in the fortunate position to have two complete independent calculations of the hadronic light by light. I note that even though this is a 4-point function, which is very, very challenging to compute in Lattice Qcd, the overall precision goals are much less demanding than for the hadronic vacuum polarization. So here now is a summary of the situation for the hadronic light by light and the hadronic vacuum polarization. Let me start with the hadronic light by light. In orange, you see the old results that are based on models of QCD and some insights from effective field theory and chiral perturbation theory, and using large NC arguments. And then there are the 2 points that are coming from Lattice Qcd. The red point here is the data-driven dispersive evaluation in the white paper. And in black, you see the result that is the white paper, final result, the white paper average. The white paper average was obtained from combining this Lattice Qcd result with the data-driven result. And you can see that the new result, of course, came out after the white paper is completely consistent with this white paper average. So we're now in a situation where, first of all, we can confirm that the old model-dependent results, actually, they got the physics right. These are, smart phenomenologists, and the light by light contribution, the true light by light contribution, is right about where they said it would be, but now the errors are quantified, and with a little bit more work, the errors will become more reliable and will be reduced. We now have two independent ways of obtaining this important quantity, and they both are in overall good agreement. So can the hadronic light by light contribution rescue the standard model? The answer is no, it cannot. It is, its value is, close to 100 times 10 to the minus 11 in these units, will stay there with an error that will become better and better. Now, for the hadronic vacuum polarization, the situation is a little bit different. In red, you see the data-driven evaluations that form the basis of the white paper. And in blue, you see the lattice computations, which have errors that are too large to actually quantitatively weigh in by the time of the white paper came out. So the white paper evaluation is then based on these data-driven evaluations with the conservative merging procedure that I showed you. By the time the white paper was finalized, the BMW collaboration posted on Archive a new computation, which has subsequently changed a little bit. What I'm showing here is the version 3 that was published in Nature a day after the Fermilab experiments announcement. And you can see that this result is compatible with a new experimental average, compatible-ish. It's about 1.5 sigma tension, and also compatible-ish, if you want, overall with the data-driven result, but in larger tension of about 2.2 sigma. And so this is a situation that has been the subject of a lot of discussion, and will continue to be scrutinized. What I would like to say here is that the BMW collaboration's result, impressive as it is, needs to be scrutinized, and we need to have other lattice calculations with commensurate precision to really make sure that all of the methods that are basically driven to the edge of the allowed precision, that that we have good agreement between different lattice results for this before we can actually draw firm quantitative conclusions from this result. So one of the ways in which we're scrutinizing the results and the tensions between data-driven and lattice results, and also between different lattice results, is by focusing on Euclidean windows in time. Recall that we compute on the lattice the hadronic vacuum polarization from this integral over Euclidean time, and we can look at windows of Euclidean time to isolate different distance scales and scrutinize them in more detail, and also understand how the different systematic errors contribute differently. So that is still something that is actively being investigated. And in particular, this reveals a large discrepancy with data-driven methods and with the BMW collaborations result for the intermediate window. The intermediate window is basically this one here. So it is not sensitive to short distance discretization effects and less sensitive to finite volume and statistical effects at large distances. So it can be computed using Lattice Qcd methods more precisely than the overall. And so there are some tensions here that need to be understood. So that is the current situation for the hadronic vacuum polarization. I would also like to point out very quickly that changing the hadronic vacuum polarization has an effect also on electroweak fits. And there is an important interplay via the dispersion relations between the hadronic cross sections, the hadronic vacuum polarization contribution to A mu, and the hadronic contributions to the running of alpha. All of these are interconnected, and having a puzzle in one, having a change in one then also implies changes in the other. And those changes would need to be understood if these tensions persist. I'm going to skip this for now, given that I'm running a little bit late. This slide is just to show you that that there is a large effort by the Lattice community. Here you can see all of the talks that were given at the Lattice conference at the end of July, and these are just the parallel and talks and posters. There were also 2 plenary talks on this topic. So this is a priority for the Lattice community to refine the hadronic corrections to A mu further from direct lattice computations. So for now, the standard model, the best standard model evaluation still is the white paper. And now we can, and so one should take this tension at face value for now. And there's a lot of work by people to explore the possible new physics scenarios that might give rise to this tension. So there's been workshops on this with many different talks. There are basically almost all of the different BSM scenarios can still be accommodated, but they are constrained. As a reminder, A mu, the anomalous magnetic moment of the muon, is different. Provides complementary constraints But the tension, this 4.2 sigma tension, if you look at the numbers, this is larger than the entire electroweak contribution. So it is large. It could become smaller and still be a good sign of new physics. And accommodating this tension in beyond the standard model theories is an active area. There's a large community of phenomenologists working on this with dozens of papers coming out almost every week. Hundreds of papers already haven't come out since the announcement of the Fermilab experiment. I would also like to point out that there is an interesting development in recent years also for the anomalous magnetic moment of the electron. The precision here is much, much larger than for the muon, of course, but there's some interesting tensions that need to be resolved. There are two different measurements of alpha that affect the standard model prediction for the electron. In the electron's case, the QED corrections are even more dominant than for the muon. The hadronic and electroweak corrections to the anomalous magnetic moment of the electron are suppressed because the electron's mass is so much smaller. But there's a 5 sigma discrepancy between two measurements of alpha leading to this situation here. So this is another space to watch. These tensions, these differences are much larger from what you would expect by naive scaling of sensitivity to new physics. And the tau lepton's anomalous magnetic moment, unfortunately, is not measured even with a precision that is close enough to be relevant because the tau lepton decays so quickly. So let me summarize the situation. QED and electroweak contributions are known very precisely. The best determination of the hadronic vacuum polarization comes from dispersive methods, which are based on well-tested experimental data. There are some really annoying tensions between the data, but there will be new improved measurements coming out from Babar, from Bell 2, from BESS 3, from the Novosibirsk experiments. So hopefully the situation of the tensions between the data will be resolved, and we will have even more precise data-driven evaluations. I showed you the first Lattice Qcd computation of the HVP with sub-percent, just about sub-percent uncertainty, 0.6%, which is, however, in tension with a data-driven approach. And wait for the Lattice community. There are quite a few different groups that are in hot pursuit of these computations, including our group. And so we will have more information soon. And all of this information will go into a new updated white paper. I also described the status of the dispersive light by light and the lattice light by light, which is basically now solved, which is wonderful. And here is the overall outlook. Without repeating everything I already said, I wanted to just point out that if, which we don't know yet, but if subsequent lattice computations reveal a tension between data-driven and lattice calculations, this is something we must understand. This affects, of course, the conclusions about where new physics is, and there will be further, there's a complementary measurement planned by the Muon E experiment, which will give us more information about a different view about in the space-like region of the hadronic vacuum polarization that doesn't use hadronic cross-sections. So that will be very important as well. I've mentioned the theory initiative. There's been, this is a large, well, large-ish, every workshop had close to 100 people that have participated in these workshops. And here you can see the photos, the last two being Zoom photos of the people that have contributed to this effort and that continue to drive progress here. And also, of course, we've received funding. So thank you very much for your attention. I'm ready for your questions. I'm going to go back to
Thank
this.
you very much. Thank you very nice. I don't know from the audience now.
I have a question.
Sorry, is there any question here? No?
Yes.
Oh, Gabriel, yeah, go ahead, please.
Okay, thank you for this nice talk, Aida.
Thank you.
I have a questions for in your slide 32.
Okay.
Okay. It seems there is a trend in lattice calculations to be higher than the dispersive approach, and in agreement with the experiment. Assume that in the future this trend is confirmed by refined lattice calculations. Is there a way to establish where the difference between dispersive and lattice calculations could come? For instance, by cutting the momentum transfer in the integration, so that you can compare different regions and discover if there is a missing exclusive channel that is not included in dispersive calculation.
Let me answer that in several parts. I pointed out to you already these windows in Euclidean time, and you can, let me see if I can, escape. Actually, what I want is, I thought I had a, okay, then I need to just describe it. Oh, here it is. Sorry. I thought it was in the appendix, but it was in the main talk. I skipped over this. So here you see the windows in Euclidean time again. And you can now take a look at these windows in Euclidean time and bring them back to root S. Okay, which is, you know, the data-driven approach. You see that, of course, there's not a one-to-one correspondence with exclusive channels directly, but you know, there's some intermingling between, you know, between Euclidean time and S. What you also know, probably, what all of you probably realize is that going from Euclidean space into Minkowski space, you know, in this case would require a Laplace transform, which is difficult to do, but the other way around is fine. So we can take experimental data, measured the cross-section data, and we can very easily turn them into measurements of the individual windows. So measurements of windows that are constrained, you know, with these weight functions. And then you can look at what the different windows that people had defined, what channels contribute. And for the intermediate window, for example, the pi channel at less than a GeV contributes only about 30%. The long distance window here, the blue window, would receive 70% of the contribution from the pi channel at low energies. So in this indirect way, you can, by looking at windows, and you can even look at, you know, smaller windows if you want, you can isolate the tensions in more detail. This has not really been done yet. You know, I showed you this. This is the intermediate window, and there's a 4 sigma tension in the intermediate window between the BMW collaboration and what you would obtain from R ratios. But there is another lattice computation that's perfectly compatible with the R ratio and in tension with the BMW collaboration. So these windows will allow us to perform more detailed cross-checks and actually seeing whether the different lattice computations agree with each other in each of the different windows, and how which have different systematic errors, and if, you know, the long distance window, say the way it is treated by the BMW collaboration, gives rise to a bias, for example. The reason why I say that is because the BMW collaboration's result requires a treatment where they first have to correct the data for the dominant discretization effects that are not describable by a linear semantic EFT description, you know, extrapolating linear and A squared. So they first correct the green points to obtain the gray, blue, and red points, and they really have to trust the correction procedure. They don't just extrapolate these results to the continuum limit because they believe that there are corrections here that are nonlinear in the lattice spacing, that are important, that are large. Okay, so the continuum limit procedure by the BMW collaboration, you know, they've tested this procedure. They believe that they are, you know, what they're seeing is correct, but it is something that needs to be scrutinized with other discretizations. Recall that different lattice actions have different discretization effects. So at finite lattice spacing, you know, different results will be very different, but they all have to have the same continuum limit. So that continuum limit should be universal. So that's one question that we need to scrutinize in very much in detail. In particular, this correction procedure would affect the long distance more than the short distance or intermediate distances. Another reason why I'm talking about this is because the interplay between electroweak fits and the hadronic vacuum polarization. If you take the BMW collaboration's result of HVP and just say that their result is larger than data-driven, and that difference is evenly distributed over the energy, over all energies, then that gives you a large difference with electroweak fits. You get something close to 4 sigma. Electroweak fits, of course, have the running of alpha has a different weight in it than HVP. The HVP, as I explained, is weighted towards low energies, whereas the running of alpha is weighted towards higher energies. So if the HVP difference comes from low energies, right, then it can be hidden in the electroweak fits, but that's something that needs to be understood. Finally, what I also wanted to show you is that one can take a look at, you know, what changes do you need in the cross-section in order to get something larger in this 1 GeV energy region. And the changes in the cross-section you need would be significant, would bring the experimentally measured cross-section in conflict with the implications from the lattice calculations. But there are further tests that one can do. There's further lattice computations, if needed, that one can do. It's too early for that, because first we need to do those other cross-checks of the different windows. And we need to see the agreement at short distances, at long distances, at intermediate distances in Euclidean space, and also understand whether or not this tension that I showed you here for the intermediate window you know, if the excess is in low energies, but the intermediate window, only 30% of it comes from low energies, and there's a 4 sigma tension, then, you know, you would get a much larger tension for the long distance window. So there are ways in which we can understand these tensions better. Some of them are a little bit less direct, but they're certainly important. But first, we need to resolve the tensions between the different lattice results.
Yeah.
You know, this is significant, this 2 sigma tension here. So I would say that to answer the start of your question here, these errors for these groups, lattice calculations, these errors are real. There are some that are large with large errors. There are some that are low that are actually, the central values are much more compatible, but the overall errors are large. These errors are real right now. Where a new lattice average centers, whether it centers here or here, we really don't know yet. It's really too soon to make I mean, that was a big if, the statement that you gave. You know, if lattice results go there. In my mind, that's a big if.
Okay, thank you.
Sorry, that's a long answer.
No, but very detailed. Thank you.
Okay, thank you very much. I've been told they have some audio issues, so I apologize in advance in case I've been trying to solve them meanwhile, but hopefully they'll be okay. I think we've lost Aida. Yeah,
yes,
we've lost.
We lost her. Let's wait for some minutes to.
Yes, let's wait.
To reconnect.
Yeah,
yeah,
you can
maybe
start
when
your juggling act, Roberto. To keep people
I don't have anything here to. No, but maybe when she stopped the screen share, she without wanting to click the leave the. Hello, Gabriel.
Hola, Roberto. Hello.
How are you?
I'm fine. You?
So.
Yeah, here is
she's back.
Aida is connected.
She's back.
She's back. So can you guys hear me well now?
Yeah, now we can hear you well.
I closed a lot of things, so it should be working. Let's see.
I'm very sorry, my laptop died. I wasn't paying attention to it telling me it was out of juice. So now I'm on the other computer. I'm sorry.
Don't worry, don't worry. You just missed us thanking for the answer. But okay, so should we go on? I don't know if there's any more questions.
There's a question in the YouTube channel. We also have a question, if I may.
Right. So I noticed a question in YouTube. So okay, I'll pass it on. So the question comes from Carlos Antonio de Souza Pires. Is it possible that this result comes down to the uncertainty in the hadronic calculation? Actually, how hard is it?
Yes, the uncertainty in the standard model prediction is completely dominated, the uncertainty is completely dominated by our knowledge of the hadronic corrections. And what we're working towards is to have 2 independent methods that can address these hadronic uncertainties, hadronic corrections in 2 completely independent ways. Right now, as I showed, there are some puzzles. They don't completely agree. I would say that the data-driven method based on experimental measurements is really well established. The experimental measurements of the cross-sections have been performed over decades. The method to turn the hadronic cross-sections into a hadronic HVP estimate of the muon and magnetic moment, those methods are pretty solid. There are some details like understanding radiative corrections and so on, but all of that work has been done, and the methods themselves don't use models. I mean, you're just summing over the channels. You don't have to describe, you know, resonance shapes and mixings between the rho and the omega, rho and photon. Nothing like that is needed because you're directly summing over all of the hadronic channels. So the amount of theoretical assumptions that goes into the data-driven method is really very small. But it is entirely driven by how well can we measure those cross-sections. And, you know, there are those annoying tensions, but those tensions are actually much smaller than the differences that I was talking about. The lattice methods are still being refined, I would say. We're still needing to understand for this really complicated multi-scale object that the hadronic vacuum polarization is, that we need to know at 0.2% precision. It's both the structure, the fact that it has all contributions from all of these different scales, and the precision demands. Both of these things make it not an easy calculation using lattice methods. But what I tried to show you is that, you know, our methods are being refined, and we are really moving very, very fast towards a time when we can have method averages of the different lattice results, and we can quantify how well the different extrapolations work and really get an understanding of the reliability of the underlying methods. So, you know, the BMW collaborations result, they did a serious computation. They did what I said needed to be done, with having many different ensembles, with having many different parameters. They did a very, very careful, impressive finite volume study. So, you know, it's a serious calculation, but it's really pushing the boundaries. And so it needs other computations using other discretizations, independent teams, and that is coming along. I think in a year, in 2 years, we will have clarity, and we will see if there's a tension between data-driven results and lattice results. It's too soon to say that there will be. Another long answer, I'm sorry. You are muted, Joel.
Yes, sorry. Thanks. I shouldn't be making these mistakes. Anyway, so there's nothing else on YouTube. So great, thank you very much.
I have a question.
Nicolas, please go on.
Okay, thanks, Aida, for the nice talk. So just out of curiosity, if you take now these BMW results, what happened to the 4.2 tension? I mean, it goes down to what, do you know?
So if you take the BMW result at face value, and so replace the white paper with the BMW result, it's 1.6 sigma tension with the experimental measurement, which is not really a tension, right? 1.6 sigma, you say, is compatible.
Okay, thanks.
But the difference between, because they're right in the middle, the difference between the BMW result and the data-driven result is a little bit more than 2 sigma, which you can also say, well, compatible. But if you go into the scale-dependent quantities, as I discussed, you have this 4 sigma tension. That's now not so different between, you know, between experiment and theory. I mean, it's you know, you can play these numbers games.
Great.
Thanks.
So via YouTube, Carlos Antonio is also thanking you for your previous answer. I don't know if there's any more more questions from the audience? Roberto?
I have a question. First of all, thank you very much for the talk, Aida. It was super interesting. So one question I was wondering is because for people that is looking for BSM, I mean, theories or whatever, these uncertainties are the most important to set up the scale of the new physics. If there is a new physics explaining the G-2. So more or less, for the point of the experimental side, how long we could wait for reduce the uncertainties? Because one part is the part of QCD and lattice that is very important, but as you said, also with the question of Nicolas, if you have 1.6 sigma in the worst scenario, but you reduce the experimental uncertainties, maybe it could
Right. So the analysis of the Fermilab experiments, so they already have data from run 2 and run 3. And those data are, I think, like twice in terms of statistics, we might expect something like twice the statistics, maybe even 3 times. And so they're analyzing those data right now. So you might expect a reduction by a factor of 1.5 or a little bit more compared to now in about a year's time, next year. And then, they will, the following year, roughly speaking, I mean, it could be earlier next year. It could be that because they've been known to be very careful and they are done when they're done, which is what they should do. So it may be a little bit later, but the data are already there. So I expect to have something like a factor of 4 reduction in the overall uncertainty, say 2025, very soon. And, in between, it'll be, in a year's time, 2 years' time, factor of 2, factor of 3, etc. That's my expectation.
So we're going to have a lot of news from the
yeah. And of course, we'll have to see where the central value goes, right? You might have noticed that the central value went down a little bit. We'll see. I mean, completely compatible, of course, but things can change within errors.
Yes. So another question, if I may, I think Gabriel want to ask something because he unmute himself, or I don't know. Anyway, just by curiosity, because this part with Lattice Qcd, which is the main, let's say, problem with the Lattice Qcd is the kind of, it need the refinement of the techniques for the QCD, or it's just, not just, but is the computational complexity of to make the calculation? I mean,
right,
or both. I don't know.
So for to get the total HVP, the correlation function at large times, has a signal over noise problem. That's well understood. We know why. We know why the statistical errors increase. So that means that computing the total HVP with high precision is computationally very expensive. And one answer as to why the BMW collaboration was able to obtain the precision they did, to put it in technical terms, is because they clobbered it. They used a lot of computational power. I mean, they also, did a good job. So, that's one answer. But the other answer is, if you look at, say, the intermediate window, you can actually do that with much less computational power, because, then you don't care about the large errors in large times. And I mean, it's pretty remarkable, the difference. But now in order to get to the precision, we really do need to also understand the continuum limit extrapolation. So this is kind of back to bread and butter. But here we're talking about, as I said, a quantity that has, you know, that is sensitive to many different physics scales. When we talk about a pion and, you know, pion decay constant, the scales, it's much simpler. It's a stable meson, and, you know, it's lambda QCD, and, you know, figuring out the, you know, I mean, the semantic EFT tells you that discretization errors are powers of lattice spacing times the relevant physics scale. So life is simpler there. And I think that all of these methods certainly work for this case. It's just when you push on the precision, then you also, you know, precision makes things harder. So now you have to understand higher order discretization effects, you know, in more detail. And really, you know, you might have, you know, from off-shell contributions, which you have here, you would have not just A squared and not just the power law, but you would also have terms that, you know, would be logarithmic in lattice spacing, and can you resolve them? So it's a matter of increasing the precision to really include all of the different variations at the needed precision. It's not new methods, it's just refining our existing methods to address the precision needs, I would say. Again, that becomes computationally also expensive in the end.
Thank you.
Okay. You okay, Roberto?
Yeah, I was just thinking.
So I don't think there's anything else from YouTube. No, nothing else from YouTube. I'd like to ask one final question.
Okay.
Because we're running out of time. But I remember many years ago that when evaluating the hadronic vacuum polarization, there was this tension between data coming from electrons and taus. Is this what
Very
you're
good.
referring to?
No. Very good. Yes. So I've completely glossed over that. So there was a tension, and some people are pointing out that if you take the old tau data, that they are, you know, agree with the BMW collaborations result, etc. When you use tau decay data, right, the tau lepton decays via virtual W boson. You know, and then the virtual W boson will decay into the hadrons, pions, etc. You know, so you might have, you know, tau plus by virtual W boson decays into pi plus pi zero, say, and pi plus pi zero, pi plus pi minus pi plus, etc. So the final state, of course, is charged because it goes via charged W boson, because you start with a tau lepton. Whereas for E plus E minus data, you're directly measuring the photon's vacuum polarization. You have a photon connecting to a hadronic vacuum bubble. The cross section is E plus E minus goes to pi plus pi minus. So it's electrically neutral. So you have to account for the isospin rotation going from basically the photon to the W boson. And now at these scales, this is not something, I mean, you can estimate it phenomenologically, but there are errors associated with that. If you include those errors, and if you do this, then basically, first of all, the tau data now are less precise because we have much better E plus E minus data. You include this correction, they weigh in much less. You know, you have an uncertainty from that, and then, you know, and then how well do you know, how well have you estimated the uncertainty? Because this is also, again, a non-perturbative problem. You know, people have tried to work on this, and the conclusion has been that the tau data are just not that useful. But there are ideas for lattice calculation of this isospin correction. Once you have something that you have calculated, that if you can calculate the isospin correction, again, non-perturbatively, with quantified errors, then you can use the tau data. And if we have, say, a tau charm factory, well, I think we have a tau charm factory also, you know, with the Bell 2 experiment, right? So then you can use the tau data, but you really have to, in order to use them quantitatively, you have to address the isospin rotation.
I see. I see. Great, thank you very much. So I don't know if there's any final questions. I don't think so. No, nothing in YouTube. No, nothing in YouTube. So okay, thank you very much for this wonderful webinar.
Thank you.
I've learned so much.
Thank you. My pleasure.
So to all the viewers, please remember that we will be having a new webinar soon. We'll be having Maximiliano Isi. I think he's probably talking about black holes, not very sure, but please stay tuned and we'll see you soon. Thank you all. Bye.
Bye-bye.